So, continuing from what we have done, what we have seen is rate of flow can be written in this manner, where this is a resistance term, R divided by MB is C, T temperature as there, diffusion coefficient. Now, this I can write, supposing this part, vapor pressure difference delta PV, del PV, and HD corresponds to all other terms, right, other than this. So, d mu and the distance across which it is. Now, this is something similar to a kind of a convective term. So, this is a convective. Now, what is convective term? Perhaps it is looking a slightly, it is for the new for you. If you remember, in case of cooling, Newton's law of cooling, the rate of cooling is proportional to temperature difference. Something analogical to this here, we will discuss that convection later on. Something analogic to here, the rate of vapor transfer or mass transfer is proportional to the vapor pressure difference. So, this is what it is, right. So, we are trying to get an expression to show that T minus dry bulb temperature minus wet bulb temperature, that is the wet bulb depression, is a function of relative humidity. That is all we are trying to do. So, you see the amount of heat that will be transferred, this is the mass transferred multiplied by latent heat of evaporation. Mass transferred was this much, mass transferred was this much. I have replaced all things by a constant h d, C t remaining here. So, d mu and d mu per unit length, that I have done, transferred into h d, equivalent as if it is per unit length. So, this vapor pressure difference is this. Now, if I want to find out the amount of heat that will be transferred because of the vapor transfer has occurred, vapor or moisture transfer has occurred, it will be related to mass, because m dot is the rate of mass transfer, mass of moisture vapor that transfers. So, the latent heat associated with this. So, if I multiply this by L, I get the rate of heat transfer associated with this. So, I simply multiply this by QL is the heat flux per unit area. So, everything has been per unit area. So, latent heat transfer I have just multiplied by latent heat, and this is this latent heat transfer I have just multiplied by this. So, amount of heat transfer is this, and this will be also equals to, from convective law of convection, if the temperature difference between the dry bulb temperature and wet bulb temperature difference is this much, right, then the amount of heat that will be transferred is given by convective heat transfer coefficient multiplied by T T W. So, therefore, T minus T W is H D divided by H, etcetera, etcetera. So, wet bulb depression is a function of the, it is related to saturation vapor pressure minus the vapor pressure. Saturation vapor, supposing I have moisture on my skin, then this is in a saturated state of affair, T W I can assume, surrounding is there is some dry bulb temperature existing, and this difference is related to the vapor pressure difference, saturated vapor pressure minus the vapor pressure difference. So, that is how we are trying to show that T minus T W is a function of this wet bulb depression, as we call it. We can estimate this also from vapor pressure, and thus the empirical relationships are possible, and I can find out. So, T by it can be written as H d by L, also related to the specific heat and density of the, this can be related to specific heat and density of the Cp stands for specific heat of the air under constant pressure. I think will be further clear when we discuss them somewhat later on. So, all that I was trying to point out here is wet bulb depression is related to the relative humidity, right. Wet bulb depression is related to the relative humidity. Okay. What is dew point? Dew point is that temperature at which moisture will become, supposing I reduce down, go on reducing the temperature of the air. Now, a point will come when it will become saturated. So, that is dew point. If you try to cool it further, actually condensation will occur. So, that is dew point. So, dew point, there is an empirical formula like this. I think I will not discuss this much. This is an empirical formula available for dew point, right. So, this is absolute, this is absolute temperature 40, 30, etc., etc. This is relative humidity minus, okay. So, this the dew point, there is I do not think I will be interested further on this at the moment. Now, we define something called specific enthalpy. What is specific enthalpy? Enthalpy is the heat content of the air, actually. We are talking of air here, and we can only measure the change in enthalpy, you cannot measure the enthalpy as such. So, we measure the enthalpy change from a relative temperature, in our case it is 0 degree centigrade. So, if the specific heat of air is Cp, temperature, absolute temperature is T, then this will be the specific component because of the dry air, its temperature being higher, mass into specific heat into temperature difference. So, it is for per unit mass. So, this is the amount of heat content of the air per unit mass, unit kg at a temperature T, and this is the moisture content, this is the specific heat of moisture vapor, and this is latent heat. So, we assume also that all vaporization takes place at 0 degree centigrade. So, if it has got some moisture content, that moisture will come from, it would have evaporated, let us say as an assumption at 0 degree centigrade itself, and it has got some heat content, that is what we are looking into, right. So, this is specific enthalpy, and all these are there in the psychrometric chart. So, if you see in the psychrometric chart, dry bulb temperature, there will be a line for specific enthalpy also related to dry bulb temperature and moisture content. So, specific enthalpy is a function of dry bulb temperature and moisture content, right. So, it is actually like this is the product, of course, G into T, but however, we have lines. So, in psychrometric chart, therefore, lines are there for specific enthalpy, the curves are there for relative humidity, saturation line and so on, which I showed you earlier. Let me see if I have, yeah, we have, I will go back again to that diagram. So, that is why you can find out if from here you can find out. So, the specific enthalpy lines are here, wet bulb temperature and dry bulb temperature is same at 100%. So, if you see this is let us say is 4 degree or this is 10 degree, and this is the wet bulb temperature is also 10 degree. So, wet bulb temperature lines are inclined like this, wet bulb temperature lines are inclined. So, this is 10 degree wet bulb temperature, 10 degree dry bulb. So, this is the temperature line. So, wet bulb temperature lines are inclined, right. They are same at 100%, vertical lines are dry bulb temperature. So, wherever when it meets that 100% saturation line, that will corresponds to 100% 10 degree, same amount of 10 or whatever temperature is, same wet bulb temperature, and otherwise it is inclined, because for lower humidity, difference between wet bulb temperature and dry bulb temperature is high. So, if you look at this line, let us say, which is at 10 degree, here at 20 degree the wet bulb temperature is 10, dry bulb temperature is something like 18 or something like that, for 0 relative humidity. So, they are inclined in this manner. Then there are specific enthalpy line, as I said, specific enthalpy lines there, So, the other lines are also there, wet bulb temperature, specific enthalpy lines. So, in psychrometric chart you might have a look at that in SP 41, I think I have given you reference, and you get that in our you get in website straight away. Most of the institution, I mean IIT Delhi is definitely a member of Indian Standard Institution. So, you in our library website you will get SP 41 and you get this one straight away. So, you can click and get it, there is no problem, but if you look at the code anyway you will get it, right. So, if you look at the code anyway you will get it, all right. So, coming back to this. So, then let us look at relative humidity we have looked into. Let us look into air velocity. We have talked of also specific enthalpy, because it is a part of the psychrometric chart. Let us look at air velocity next. Temperature we have looked into, and quickly I have told you how you can do the measurement, and then relative humidity I talked of, and I said that if you know wet bulb temperature, you can find it out from psychrometric chart, or some empirical equations are there, which I just showed you, but I think I will solve a problem sometime so that it becomes clear better. Next parameter is air velocity. Now, it is measured with anemometers, right. There are of course very common is what is called hot wire anemometer. So, basically nothing but a small, this is a base, and you will have a small resistance, right. Now, this will be connected in, you got to measure the resistance. As you know, resistance will change with temperature, right. So, what is done is this is exposed. One can use two principles, and it is a part of an arm of Wheatstone bridge or whatever bridge it is, resistance measuring system. Now, if I pass a constant current through it and air velocity changes, then this temperature of this one will come down, because it will get cooled by air stream. Now, temperature will come down, same current I am trying to pass, or I can maintain the same temperature by changing the current. Means resistance, keep the resistance constant, change the current. So, that current is a function of the air velocity itself, or if I am measuring the resistance change because of a constant current, the change in resistance is a function of can be correlated to the air velocity. That is in a gross manner, that is the kind of principle hot wire anemometers uses, and they can be used versatile, 0 to 30 meter per second. So, you can use them inside the room and even outside for wind velocity measurements, but has to be sturdy. But then you would have seen cup anemometer, vane anemometer, you might have seen on building top cup anemometers, so they will have 3 cups, right, and they will rotate. Okay. So, as the wind velocity causes them to rotate, or windmills. So, these are the ones. So, largely one can measure with anemometers. There is something called a kata thermometer. A kata thermometer also measures air velocity, because if the air flows, there could be a depression in the apparent depression in the there can be apparent depression. Now, velocity varies from ground level to the height, because you would have done a course on loads, wind load. I am sure many of you would have done a course on wind load, and if you have done that, you would have remembered that we measured the wind velocity at 10 meter height, right, and you have K1, K2, K3 factors multiplying for the load. Now, one of them is related to topography. So, as the topography changes, this height will change. The velocity near the boundary, ground boundary is 0, it increases, and a height beyond which it does not increase further, we call it gradient height. So, wind velocity varies with height. So, we measure at 10 meter. So, 10 meter is where a meteorological department will measure air force stations and all those air bases or airports, they measure because they need it, aviation people. So, 10 meter is height where it is measured, but there is something called gradient height. So, as you go up, it increases and becomes constant at a given point, which we call as gradient height. Precipitation and rainfall is the other feature. Precipitation is what? It is both snow, rain, everything put together, we call it precipitation. And driving rain index is very important in certain type of climate. Rainfall intensity, we would like to protect the building from rain as well. So, in certain, for example, if you come from Kerala or northeast in India, you have a lot of rainfall, and therefore, and wind driven rain as we call it, it would like to push it inside into the room or space that so wind driven rain is important. Not only that, it would when it impinges on your wall, the moisture can penetrate through the wall. So, design against such kind of moisture movement is wind driven rain is a factor. Although we will not discuss this in our class, wetting and drying condensation or moisture movement in building materials or walls or building envelope. We will not talk about that in this class, but this is a parameter, important parameter. Now, what is WDR? WDR is actually is the intensity of rainfall multiplied by rainfall intensity multiplied by the wind velocity, some factor multiplied by wind velocity, right. So, WDR is wind driven rain. So, this is important, but precipitation itself is important to classify the allocation or it's which zone of climatic class it belongs to. Without going to the climatic classification right now, which I will come to a little bit later on, as you can understand, those who have come say like Delhi has got a climate which in the month of May and June, if you are here, it would be very, very dry and very hot, about 42, 43 degrees centigrade sometime. And if you compare that with, let us say, Mumbai, where there is a lot of rainfall, the temperature do not go that high, but the humidity is very high. So, you see, when you are designing your building for functional purposes, thermal comfort, you got to take these aspects into account. You got to take these aspects into account. All right. So, therefore, we can classify these places according to their climatic situations. I will come to climate later on, and that's why those parameters of the through which we classify the climates or parameters or factors of environment, that is what we are discussing one by one. First we discussed temperature, then relative humidity, air velocity, and now just now I mentioned about precipitation and rainfall, right. So, this is called wind driven rain. There is a formula for wind driven rain, V0, 0.22. This is given by one Lacey, Mr. Lacey, from IHB guide, Institution of Heating and Ventilation Engineers, England. He published this this equation there, its guideline, it was available. Now they call it Chartered Institution of Building Services Engineer. So, whatever it is, V0 is 0.222 W, where this is the wind velocity, R is the rainfall intensity to this, an empirical equation. So, that gives you the flux or rain flux. Again I said I will not discuss wetting and drying, that can be 42 hours lectures is not sufficient for that. But I wanted to introduce these parameters to you when we are looking at the subject. So, desirable air and radiant temperature, relative humidity, airflow, air velocity, control through proper choice of proper orientation, envelope, fenestration design. So, all these aspects, air temperature or temperature coming from the hot surfaces of the building, relative humidity, etc., etc., I can actually control somewhat through proper design of the envelope. Now, what is building envelope? It is basically, there is a formal definition, I may give you in the next class if possible. Formal definition is defined in some codes actually. So, it is the basically everything that is in contact with the surrounding environment, just immediate interaction of the surrounding environment with the building envelope. So, which will include in fact the sunshades and things like that, the walls and the roof and so on. So, I can design that, also design the fenestration. Now, what is fenestration? It is the openings which are left by choice, by design, for daylighting and ventilation purpose, natural ventilation purpose, right, as opposed to infiltration, which is not by choice, by default. For example, leakages through the gap in the window does not close, does not seal, there will be some gap. So, air can enter through that is infiltration. So, infiltration is not by design, it is by default, poor construction, etc., etc., while this is by design, fenestration is by design, right. So, proper orientation, etc., etc., and we will look into, in this course we will look into all these issues. Proper glare free lighting through daylighting, that is what is another aspect we should look into. Glare free lighting, now glare I will define again later on, but quickly, glare occurs when you are looking to the car headlight, do not see anything, it is called disability glare, you do not see anything, but the glare can be a kind of discomfort glare also, which can happen in a classroom sometime. We will discuss that sometime. Later we design the illumination, task illumination for writing, for example. If the light is not sufficient, you will not be able to write, right. Contrast between, say, this is blue in color, this is black in color, and background is white. So, there is a contrast. Now, when I am making the slides, if I make it yellow, you will not be able to read it, right. The contrast has to be there, or if the background was by and large blue and I have written black, maybe you will not see it so well. So, the contrast is important, brightness, contrast, illumination design takes care of all those. And noise control, privacy through various kind of zoning, planning, barrier design, insulation, and acoustic design. I will talk about this. So, this is what we will cover in this particular course in general, and just now I talked of environmental features, measurable features through which I define the environment, right. So, I think after that we can look into thermal issues, and in that context I must look into earth energy balance. A part of this is available in a book written by Sozole, Kenigsberger and all those. Right, they are given in the reference cheap book available, you can look into it, right. So, also I have a written lecture notes on the subject typed out, given to previous year's batch, you can look into that, right, and it is available, written material is available, maybe I will upload it sometime. So, in order to look at the thermal issue, I should look into earth energy balance, and you must be hearing about global warming, quite a bit of it now. So, this might be relevant to that. You see, at the top of the atmosphere we get 100%, supposing I get 100% solar radiation. Now, what happens is, if you look at it, some of it directly 50% is received to the ground, some of it will go away, reflected away, straight away at the top of the atmosphere. Now, this is 4, and number 4 is 20% by evaporation loss. Moisture is there at the ground level, C is there, so evaporation loss, and this is this is 50% is absorbed. Each one of them we will look into. 50% is absorbed in the atmosphere itself, right. 50% is received. Out of this 50%, some goes out reflected directly, and some of it will be absorbed in the atmosphere. Now, there is a terminology 20% long wave radiation. You see what is long wave radiation, that is what it is. So, if 50% is received, 50% is absorbed in the atmosphere. Part of it will go back straight away, and part of it will come to the ground and get reflected, right. Finally, of course, you can understand there is a periodicity in the whole thing, annual periodicity. Every year we receive energy from the sun, right. Whatever you receive today, 365 days later you are likely to receive similar kind of thing, not exactly same, but it is likely similar, almost similar. So, there is a annual periodicity. Now, this whatever energy the earth is receiving over that cycle, it must be dissipating out the same, otherwise temperature of the earth would have increased over these years, and by the natural process, and the temperature would have increased, but this is not happening. Well, what is being said now is that because you have got a layer which allows what are called greenhouse gases, which allows sun's radiation to come in, but does not allow radiation from the earth to go out, therefore, there might be some kind of a global warming scenario. So, that is where the long wave terminology becomes important. Maybe just I will talk about that in more details later on, but maybe just quickly introduce. You see, sun's radiation belongs to wide range of wavelengths, starting from ultraviolet, visible range, right, then infrared radiation, red infrared radiation. So, if you look at all of that, which we will look at some time, if you look at all of them, a part of it is only visible light, A good lot of it is infrared region, that's actually heat radiations. They are heat radiation, and longer wavelength is more, right. Now, the characteristics of the radiation that comes from a body depends upon the temperature at which it is radiating. So, sun radiates at very high temperature, million degrees centigrade, etc., fusion process and so on. Therefore, sun's radiation is of that variety. They are short wave to long wave radiation, visible radiation, everything. While if you look at Earth, the cosmos is cool. So, radiation heat exchange always takes place between hot and the cool bodies. Earth itself is warm compared to the outer cosmos. So, it will also radiate the heat. Now, this quality of this radiation depends upon the temperature of the Earth, terrestrial radiations. So, these are all long wave radiation. You do not see that radiation, but they are heat radiation. For example, you have a hot plate here which is not glowing, but it is just hot. You can still feel the heat. You do not see the radiation. If you are close to some hot plate which is not really red hot, no color change is occurring, still you can feel the heat because the infrared radiation that is occurring. So, bodies at lower temperature radiate long wave radiation, right, and that is what we are talking about. So, terrestrial radiations are all long wave radiations. For example, radiation heat exchange between the roof ceiling of this room, if it is at different temperature than my skin temperature, that would be actually all long wave radiation heat transfer. So, it is all long wave radiation heat transfer, and some gases like carbon dioxide, methane, etc., at the top of the atmosphere, if they are there, moisture vapor, they do not allow long wave radiation to go, but they do allow short wave radiation to pass in, like glass does. So, we will discuss about that later on. And when such thing is occurring, the sun's radiation can come in, but the earth's radiation cannot go back, and that is why this this concern about that global warming. Anyway, but for our purpose, we look into this because this has something to do with our temperature outside climatic zone and things like that. All right. So, I think we will stop here for the day and start from earth energy balance in the next class. Okay. Thank you very much.